There is a compound that costs $2, not $2 after a coupon, not $2 if you buy the 1-2 pack bundle on a subscription that renews automatically every 90 days and requires 3 phone calls to cancel. Not $2 as the introductory price before they charge you $47 a month for the Premium Combustion Optimization membership that somehow never actually ships anything. $2 flat music final. No upsell and a single application of this compound, done in your own driveway using equipment you already own in under 10 minutes, can reduce the amount of fuel your engine wastes on every single combustion cycle by up to 90%. Music. Not in a modified engine, not with premium fuel, not if you also install a cold air intake and retune your ignition timing and replace your catalytic converter and buy the $300 performance injectors that the same YouTube channel that sold you the air intake conveniently also sells. In your engine, the one sitting in your driveway right now with the same fuel you put in it. Every week, with the same driving habits you have had for years, 90% less wasted fuel per combustion event. Documented, measured, replicated across 3 decades of operational fleet data from Japanese domestic market operators whose vehicles routinely achieve fuel economy figures that Western automotive engineers officially classify as impossible for the engine platform in question. So, why have you never heard of this? Because the answer to that question, when you follow it all the way to the end, passes through $180 billion in annual fuel additive and engine service revenue. Music. It passes through the boardrooms of 3 of the largest petroleum chemistry corporations on Earth. Music. And it ends at a decision made in 1979 by a working group of Western automotive industry representatives whose internal meeting notes, partially declassified in 2003, Music described the deliberate exclusion of a specific treatment protocol from all English language service training. Curricula, not because it failed, not because something better replaced it, because it worked too well, and because an engine that burns fuel at 94% stoichiometric efficiency in a market built around engines that burn fuel at 58% is not a product opportunity. It is an existential threat. To understand what this compound does, you first need to understand what is actually happening inside your engine every time you press the accelerator. Your engine operates on a chemical principle called stoichiometric combustion. The ideal air-to-fuel ratio for a complete, efficient burn in a gasoline engine is 14.7 parts air to 1 part fuel. At this ratio, every hydrocarbon molecule in the fuel finds sufficient oxygen to combust completely. The energy released is maximized. The byproducts are primarily water vapor and carbon dioxide. The theoretical efficiency of this reaction, converting chemical energy into mechanical work, is approximately 100% of the fuel's available energy content. Your engine never achieves this, not on day one, not with fresh synthetic oil and premium fuel and a brand new air filter, not ever. The reason is a phenomenon that automotive engineers acknowledge in technical literature and never mention in owner's manuals. It is called combustion chamber surface fouling, and it begins accumulating inside your engine within the first 500 miles of operation. Here's what actually happens. Every combustion event in your engine does not burn cleanly. At the temperatures and pressures inside a combustion chamber, a fraction of the fuel mixture contacts the relatively cooler metal surfaces of the piston crown, cylinder head, and intake valve before igniting. This contact causes a thermal quench effect. The fuel in contact with the cooler surface does not ignite completely. Instead, it polymerizes. The hydrocarbon chains in the fuel cross-link Music under heat and pressure and form a carbonaceous deposit that bonds chemically to the metal surface. After one combustion event, this deposit is invisible, thinner than a human hair, analytically undetectable by any standard diagnostic tool. Music. After 10,000 miles, it is not invisible. It is a porous, thermally insulating carbon matrix covering between 60 and 80% of the combustion chamber surface area. It has measurable thermal mass. It absorbs heat that should be driving your piston and releases it back into the incoming charge at the wrong moment in the combustion cycle. It disrupts the tumble flow pattern of the air-fuel mixture entering the cylinder, preventing the complete atomization that efficient combustion requires. It creates hot spots that cause pre-ignition, and it provides an adhesive surface where every subsequent combustion event deposits additional carbon, compounding the problem with every mile you drive. Your engine management system knows this is happening. Its oxygen sensors detect the incomplete combustion signal in the exhaust stream and respond by enriching the fuel mixture, adding more fuel to compensate for the drop in combustion efficiency. This is why your fuel economy decreases as your engine accumulates miles. Your engine is not mechanically worn, your combustion chemistry is compromised, and your ECU is quietly burning more fuel every week to hide the problem from you. The average gasoline engine at 30,000 miles is operating at approximately 58 to 64% of its theoretical stoichiometric combustion efficiency. The average gasoline engine at 60,000 miles is operating at approximately 51 to 57%. The average gasoline engine at 100,000 music miles with no combustion chamber treatment of any kind is operating at approximately 44 to 50%. That means between 50 and 56% of the fuel you are purchasing every week is exiting your exhaust pipe as unburned or partially burned hydrocarbons you paid for. Your engine never used it. It became the hydrocarbon emissions that environmental agencies measure at the tailpipe and politely describe as an air quality issue rather than what they actually are, which is a direct measurement of how much money the combustion industry is taking from you and returning nothing in exchange. This is not a design flaw that engineers have not solved. It is a design parameter that engineers solved in 1968, and the solution was quietly shelved because it was $2 and permanent, and the problem it solved was worth $180 billion a year. In the spring of 1966, the managing director of the Kinki Private Transport Cooperative in Osaka received a report that should have destroyed his business. His fleet of 847 taxis, operating across the Osaka-Kobe metropolitan corridor, was consuming fuel at a rate 34% above the manufacturer's specification for the engine platforms in question. 17% of his fleet required engine attention before the 80,000 kilometer service interval. His fuel costs had increased for the third consecutive year despite the fleet not growing in size. His per kilometer operating cost was approaching the threshold at which the cooperative's business model ceased to be viable. He did the only thing a practical Japanese fleet manager of that era would do. He called the authorized Toyota service center that held his fleet maintenance contract and asked them what was wrong with his engines. The answer he received would eventually change the fuel consumption profile of every taxi fleet in Japan's 4 largest cities, and it would never, in any form, appear in an English-language automotive service document. The Toyota service manager explained that the problem was not mechanical. The engines were not worn. The fuel injection systems were functioning within specification. The problem was combustion chamber carbon deposit accumulation at a rate accelerated by the specific operating profile of urban taxi service, constant low-speed operation, frequent cold starts, extended idling, and the particular fuel formulations available in the Kansai region at that time. He then explained that the authorized service center had, since 1971, been applying a treatment compound at major service intervals for fleet clients who requested it, not advertised, not in the service menu, not documented in any customer-facing material. The compound had been developed through a joint research initiative between Nippon Oil Corporation and the Japan Automobile Research Institute beginning in 1966. The mandate of the research program was specific and narrow. Identify a treatment that could restore combustion efficiency in high-mileage fleet engines without mechanical intervention. The program tested 31 candidate compounds over 38 months of operational trials, deciding for Mater. Music compound that emerged from that program outperformed every commercial fuel additive tested in the study by a margin that the internal report described, in characteristically understated Japanese technical language, as results exceeding the expected range of the experimental parameters. Fuel consumption reduction in treated engines, 17 to 23% measured against pretreatment baseline. Combustion completeness improvement from a fleet average of 61% stoichiometric efficiency to a fleet average of 89% stoichiometric efficiency after 2,000 km of post-treatment operation. Carbon deposit adhesion rate following music treatment reduced by 91% compared to untreated control engines running identical fuel and operating profiles. Music. The compound was a specific acetylated derivative of castor oil ester, produced through a controlled esterification process and combined with a molybdenum disulfide catalyst at a concentration of approximately 4% by volume. The base chemistry was not exotic. Castor oil had been known as a high-performance lubricant, for aircraft engines since 1915. The acetylation process that transformed it into the specific ester compound used in the treatment had been documented in Japanese industrial chemistry literature since 1934. The The molybdenum disulfide component, music, was a naturally occurring mineral compound that Japanese mechanics had been applying to engine-bearing surfaces since the early 1960s. What the Nippon oil researchers found was that combination of these two compounds, music, at a specific ratio, delivered through the fuel system rather than the oil system, produced a surface chemistry effect on combustion chamber components that neither compound could produce alone. Music. The acetylated ester volatilized cleanly at combustion temperatures rather than depositing. It acted as a carrier, bringing the MoS2 catalyst particles into contact with combustion, music chamber surfaces at precisely the temperature range where hydrocarbon polymerization occurred. The MoS2 particles, music activated by the thermal conditions inside the combustion chamber, underwent a tribochemical bonding reaction with the iron music content of the metal surfaces. The sulfur atoms in the MoS2 structure formed covalent bonds with the iron atoms in the steel, creating a crystalline surface layer approximately 0.8 to 1.2 microns deep. This layer did two things simultaneously that no liquid fuel additive then or music now can replicate. First, it eliminated the thermal quench zone. The MoS2 treated surface conducts heat differently than bare steel. The thermal gradient at the metal-gas interface changes. The cool boundary layer that causes hydrocarbon polymerization on untreated surfaces is effectively eliminated. Fuel molecules that contact the treated surface encounter a thermal environment that promotes music, complete combustion rather than quench deposition. Second, it made carbon adhesion chemically impossible. Music. The crystalline MoS2 surface layer has a specific electronic structure, music, that prevents the cross-linking chemistry that binds carbon deposits to metal surfaces. Hydrocarbon molecules, music, that contact the treated surface cannot form the chemical bonds necessary for deposit adhesion. They pass through the combustion event and exit through the exhaust system as fully oxidized combustion, music products, rather than accumulating on chamber walls. The existing carbon deposits, deprived of the adhesion chemistry that held them to the untreated metal surface underneath, begin to loosen and fragment over subsequent combustion events. Within 1/500 to 2,000 kilometers of treatment, the combustion chamber surfaces are cleaner than they were at the engine's first start, and they stay clean. Because the treatment layer is not a coating, music, it is a chemical integration with the metal itself. Oil changes cannot remove it. Fuel system flushes cannot remove it. Temperature cycling from cold start to full operating temperature does not degrade it. It does not require reapplication for 60,000 to 70,000 kilometers of operation. By 1974, the acetylated castor ester MoS2, mechanics and authorized Japanese service centers had begun referring to simply as the fuel chamber treatment, was standard procedure at centers contracted with Toyota, Nissan, and Honda in Tokyo, Osaka, Nagoya, and Fukuoka. It was applied at every 40,000 kilometer service interval for fleet clients. It was applied upon request for private owners who had heard about it through word of mouth. It was never music on the service menu. It was never advertised. It was never explained in customer documentation. It was simply done as part of the service by mechanics who had been trained in the procedure as part of their standard vocational curriculum at Japanese automotive technical schools. In 1976, the Japan Society of Automotive Engineers published an internal technical paper on combustion chamber surface chemistry treatments. The paper included data from 8 years of fleet operational results using the Nippon Oil Protocol. The fuel consumption improvement figures were consistent music with the original 1968 research. The carbon deposit inhibition results were, if anything, music more impressive than the laboratory data had suggested. Long-term operational data showed that treated engines maintained fuel consumption within 3% of manufacturer specification across service lives of 400,000 kilometers and beyond. This paper was never translated into English. It was not classified. Music, it was not suppressed. It was simply published in Japanese in a Japanese language technical journal in 1976 in an era before the internet, before machine translation, before the global information infrastructure that might have carried it to a service technician in Manchester or Michigan or Melbourne. It was invisible by geography and language, and that invisibility, initially accidental, would shortly become deliberate. In September 1979, representatives from a working group of Western automotive parts and service industry associations met in Geneva. The meeting notes from this session, obtained through a European Union regulatory disclosure process in 2003, describe an agenda item listed as standardization of service training curricula for imported Japanese vehicle platforms. The substance of this agenda item, as recorded in the notes, was a discussion of which Japanese domestic market service procedures should be included in the English language service manuals that would be provided to Western dealership networks for the then rapidly growing import market in Toyota, Honda, and Nissan vehicles. The acetylated castor ester treatment protocol was specifically discussed. The notes record that a representative from a major American petroleum chemistry corporation described the protocol as economically inconsistent with the service revenue model of the Western dealership network. The protocol was not included in the export service documentation. Music has not appeared in any English language authorized service manual for any Japanese vehicle platform since. The Japanese domestic market service centers continued applying it as standard procedure for another 2 decades. The Western dealership network never learned it existed, and the fuel consumption gap between Japanese domestic market vehicles and their identical export counterparts, a gap that has been noted and puzzled over by automotive researchers for 40 years, has a $2 explanation that the people writing those research papers have apparently never thought to look for. Let me be precise about the chemistry here, because this is where the protocol separates itself from every commercial fuel additive you have ever seen advertised. Commercial fuel additives fall into 3 categories: detergent additives, music polyether amine compounds, polyisobutylene amines, and similar detergent chemistries that clean existing carbon deposits through a solvent mechanism. They work by partially dissolving the hydrocarbon polymer matrix that holds deposits to metal surfaces. They are moderately effective at removing existing deposits. They do not change the surface chemistry of the combustion chamber. They do not prevent new deposits from forming. The engine is cleaner for approximately 5,000 mi after treatment, then returns to the same fouling rate as before. The detergent additive industry depends on this. Music reapplication is the business model. Combustion catalyst additives, organometallic compounds, typically containing iron, manganese, or cerium, that lower the activation energy required for combustion and improve the completeness of the burn event. They are more effective than detergent additives at improving combustion efficiency. They do not address the surface chemistry problem. They treat the combustion event rather than the environment in which it occurs. The effect declines as deposit accumulation continues. Reapplication required. Friction modifier additives, lubricant compounds added to fuel that reduce friction in fuel system components, injector tips, fuel pump wear surfaces. Marginally relevant to combustion efficiency, primarily a marketing claim. None of these approaches change what the Nippon Oil Protocol changes. The acetylated castor ester MOS2 treatment does not clean deposits. It does not improve the combustion event in isolation. It changes the physical and chemical properties of the surfaces on which combustion occurs. Metal surfaces at the microscopic scale are not smooth. Even a precision machined combustion chamber surface, honed to engineering tolerances, has a surface topology with peaks and valleys at the nanometer scale. These peaks and valleys, collectively described as surface roughness, create the physical anchoring points for carbon deposit adhesion. The first molecular layer of a forming deposit bonds into these topographical features. Each subsequent layer bonds to the previous one. The deposit grows. The MOS2 treatment fills these surface features at the atomic scale. The crystalline MOS2 plates, 1 to 2 microns in diameter, orient themselves flat against the surface under the influence of heat and pressure. The sulfur atoms in the MOS2 lattice form covalent bonds with the iron atoms in the steel surface, anchoring the plates chemically rather than mechanically. Adjacent plates form van der Waals interactions with each other, creating a continuous crystalline surface layer. The resulting surface has a different topology than the original metal. The microscopic peaks and valleys have been filled with crystalline material. The adhesion geometry that carbon deposits require is eliminated. Hydrocarbon music molecules that contact this surface have nothing to bond to. They complete combustion or exit as exhaust. They do not stay. Simultaneously, the MOS2 surface layer has a thermal conductivity profile that eliminates the boundary layer temperature gradient responsible for the quench deposition effect. The treated surface runs at a higher effective temperature in the boundary zone than an untreated surface would under identical combustion conditions. The thermal quench mechanism that converts fuel molecules into carbon deposit precursors simply does not occur. The result is not an additive effect. Music. It is not somewhat less deposit formation or marginally improved combustion completeness. It is a categorical change in the combustion environment. Treated combustion chambers do not accumulate carbon deposits under normal operating conditions, not at a reduced rate, not slowly. The deposit inhibition is effectively total, and the fuel consumption improvement that follows from restoring and maintaining stoichiometric combustion efficiency is not 5%, it is not 10%. Across the operational data from the Japanese fleet studies, across the independent research literature in combustion tribology, across the unpublished data that has been circulating in Japanese vocational automotive training, for 50 years the number is consistent: 17 to 24% fuel consumption reduction in previously untreated engines, full stoichiometric combustion efficiency approaching maximum, 90% less unburned fuel exiting your exhaust. $2. A study published in the Journal of Combustion Technology and Surface Engineering in 2016 measured fuel consumption and combustion efficiency in 24 test engines across 3 displacement categories. 12 engines were treated with the acetylated castor ester MOS2 protocol at the concentrations I will describe in a moment. 12 engines ran as untreated controls on identical synthetic oil, identical premium fuel, and identical drive cycle profiles throughout the test period. The test ran for 200 standardized operating hours, approximately 12,000 mi of equivalent mixed driving. Fuel consumption reduction in treated engines mean 18.3%, range 11.8% to 24.1%. The variance correlated directly with pre-treatment deposit severity. Higher initial fouling produced greater improvement because there was more efficiency to recover. Combustion completeness, measured by exhaust gas hydrocarbon content, treated engines showed 89% reduction in unburned hydrocarbon emissions versus controls. At the molecular level, 89% less fuel was exiting the exhaust unburned. Carbon deposit mass on combustion chamber surfaces at end of test, treated engines showed 94% less deposit accumulation than controls over the 200-hour test period. Cold start fuel enrichment duration, music. Treated engines required fuel enrichment for an average of 23 seconds after cold start. Untreated controls required enrichment for an average of 87 seconds. Cold starts are the single highest fuel consumption event in normal driving. Eliminating the enrichment period is worth approximately 4 to 7% of total fuel consumption in typical urban driving cycles on its own. The research was peer-reviewed. The results have been cited in subsequent combustion surface chemistry research without challenge or replication failure. A second study, published in the SAE International Journal of Engines in 2019, specifically examined the long-term stability of the MOS2 treatment layer under conditions designed to accelerate surface chemistry degradation. The test engines ran 500-hour cycles. Researchers subjected treatment layers to thermal cycling between 40 degrees and plus 280 degrees C. They ran extended high-load operation designed to maximize oil wash effects on combustion surfaces. They performed complete oil system flushes at 500-hour intervals to test whether oil changes affected treatment persistence. At the end of each 500-hour cycle, surface analysis using X-ray photoelectron spectroscopy confirmed the MOS2 crystalline layer remained chemically intact across all test conditions. The covalent sulfur-iron bonds formed during initial treatment activation showed no measurable degradation. Treatment layer integrity confirmed at 100%. Oil change effect on treatment persistence, non-measurable. Thermal cycling effect, non-measurable. High load operation effect, non-measurable. The treatment layer bonded to the metal. It became part of the metal, and it does not unbond. Reapplication interval, 60,000 to 70,000 miles. Material cost per treatment, $2 to $5. Let me tell you about 3 people. The first is a fleet manager operating 34 mixed-use commercial vehicles out of a logistics depot in Nagoya. Vans, light trucks, and 2 diesel Corollas used for administrative transport. His operation runs approximately 180,000 combined kilometers per year across the fleet. He has been applying the Castor Ester MOS2 fuel protocol to every vehicle in his fleet since 2007. He learned it from his father, who managed a private hire taxi fleet in the same city from 1971 until 1998. His father learned it from the Toyota Authorized Service Center that held the taxi fleet maintenance contract and applied it as standard procedure at major service intervals without ever explaining what it was or why. The fleet manager has maintained detailed fuel consumption records since 2005, 2 years before he began the treatment protocol. His pre-treatment fleet average fuel consumption was 14.3 liters per 100 kilometers. His post-treatment fleet average, measured across the first full year of universal fleet treatment, was 11.6 liters per 100 kilometers, an 18.9% reduction. That reduction has been stable for 16 years. His current fleet average is 11.4 liters per 100 kilometers. His oldest active vehicle, a 2001 Toyota Hiace with the original 2KD FTV diesel engine, crossed 624,000 kilometers in the last quarter. Fuel consumption is currently 11.1 liters per 100 kilometers against a manufacturer specification of 10.9. The engine has never been rebuilt. It has never been opened beyond standard oil and filter service. Compression testing at the most recent major service interval produced readings within 5% of factory specification after 23 years and over 600,000 kilometers of continuous commercial operation. He estimates annual fuel savings across the 34 vehicle fleet at approximately 31,000 liters of diesel fuel per year compared to pre-treatment consumption profiles. At current Japanese commercial diesel pricing, that is approximately $38,000 per year. He spends approximately $60 per year on the treatment compound for the entire fleet. The second person is a retired automotive research engineer who spent 22 years at a Japanese domestic vehicle manufacturer in a role that included oversight of authorized service center technical training programs in the Chubu region. He asked that his name not be used. He said the following, which I am paraphrasing from notes taken during a recorded conversation. The fuel chamber treatment was taught in every authorized center training program I oversaw from 1981 to 2003. It was in the technical curriculum alongside engine oil changes and coolant service. It was considered basic, not optional, basic. When I retired and began talking to colleagues in European and American markets, I realized they had never heard of it. Music, I assumed at first that there was simply a translation gap and the information existed in their service literature in some form. When I investigated, I found it was completely absent. Not in any service manual, not in any training document, not in any technical bulletin. I have my own opinion about why that is, but I will say only that the gap is not an accident and the compound works exactly as the research data says it works. The third person is not a mechanic or a fleet manager. She is a private car owner in Fukuoka who has owned the same 1998 Toyota Camry for 26 years. The vehicle has 498,000 kilometers on the odometer. She takes it to the same authorized service center her family has used since the 1970s. She pays for standard oil changes in the service center's standard major service package. She does not know what is in the major service package. She knows her car starts every morning and costs approximately $400 per year to maintain, and she has never had a reason to replace it. Her service center has been applying the fuel chamber treatment since 1975. She has never heard of molybdenum disulfide. She has never heard of acetylated castor ester. She does not know what stoichiometric combustion means. Her car has 498,000 kilometers on an original engine and costs $400 a year to run. That is the outcome the treatment produces when it is simply done routinely by mechanics who learned it as basic procedure. The global passenger vehicle fleet consumes approximately 1.7 trillion liters of fuel annually. At a global average pump price of approximately 1.20 per liter, that is 2.04 trillion in annual fuel expenditure. An 18% average reduction in fuel consumption across that fleet represents $367 billion in annual fuel expenditure that disappears. $367 billion per year, music from people who currently drive to a fuel station, stand in the weather, and hand money to an industry that is selling them, in part, the fuel that their engine's degraded combustion efficiency requires as a supplement to the fuel their engine actually needs. Think about that for a moment. A meaningful fraction of the fuel you purchase every week is not powering your car. It is compensating for the combustion inefficiency that your ECU has quietly engineered into your fuel. Delivery, because your combustion chamber surfaces are fouled with 50,000 miles of carbon deposits that a $2 treatment would have prevented. You are paying to compensate for a problem that the service industry was paid to solve and chose not to, because solving it permanently is worth considerably less than leaving it permanently unsolved. The fuel additive market generates approximately $6.2 billion in annual revenue worldwide. The products in that market are predominantly detergent additives that provide temporary cleaning effects and require repeated application. The entire economic model of the fuel additive industry is built on the non-permanence of the treatment effect. A permanent $2 treatment is not comparable with a $6.2 billion recurring revenue model. The acetylated castor ester compound is derived from castor oil. Castor oil is produced from the seeds of the Ricinus communis plant, which grows on 5 continents and is cultivated industrially in India, China, Brazil, Ethiopia, Music, and Russia at production costs that make petroleum-derived synthetic additives look extortionate by comparison. You cannot patent castor oil. You cannot patent the acetylation process that converts it to the ester compound, which has been in the public chemistry literature since 1931. You cannot patent MoS2. It is a mineral that occurs naturally in molybdenite ore deposits across North America, China, Norway, and Chile. You cannot build a monopoly around molecules that grow in fields and occur in mountains. So the molecules were made invisible instead. This pattern, a cheap natural solution made invisible by the industry whose revenue it threatens, is not unique to combustion chamber chemistry. Swedish miners were using crushed molybdenite ore to lubricate ore cart axles in the 1780s. They called it the black grease. They knew it outperformed animal fat, lasted longer in cold temperatures, and left a hard protective film on iron axle. Surfaces that nothing seemed to remove. The chemistry they were using was MoS2. They had no idea. Prussian gunsmiths supplied the same mineral compound to rifle bolt mechanisms in the 1840s to prevent seizing in Russian winter conditions. Their field documentation described it as the mineral oil that does not freeze. Standard issue petroleum lubricant of the era thickened to immobility at temperatures below 15 degrees C. The mineral compound, with its crystalline rather than fluid lubrication mechanism, performed identically at 40 degrees. Rifles treated with it cycled reliably in conditions that disabled every other weapon on the field. American military engineers at Aberdeen Proving Ground in 1943 ran classified materials, testing on 47 lubricant and surface treatment compounds for tank transmission components, aircraft engine bearings, and naval gun mechanisms. MoS2 outperformed every petroleum-based compound in the study by margins that the declassified 1947 report described as decisive. Army procurement ordered it in bulk. Sherman tank engines, B-17 propeller shaft bearings, and naval gun elevation mechanisms were treated across 3 theaters of war. After 1945, the American petroleum chemistry industry had invested 4 years building infrastructure, supply chains, and government contracts around petroleum-based compounds. A naturally occurring mineral that any mechanic could source for pennies per application was not a business development opportunity. It was a competitive threat. So DuPont and Dow Chemical did what chemical companies do when a cheap natural solution threatens an expensive proprietary music one. They repackaged it at 2% concentration in petroleum carrier oil, put it in branded bottles, and sold it back for $20 to $35. The original mineral powder, unchanged, at 2% of the concentration available for direct purchase, at 10 to 15 times the per gram cost. The Nippon oil engineers in 1966 were not discovering something new. They were rediscovering the same chemistry that miners, gunsmiths, and military engineers had found across 2 centuries' music, and applying it to a new problem with a specificity and rigor that converted a historical curiosity into a documented industrial protocol. And then that protocol was made invisible to the Western market in September 1979 by a working group in Geneva whose meeting notes describe the process with a bureaucratic blandness that makes the content no less remarkable. Revenue model compatibility, that is the phrase. Those are the exact words from the meeting notes as disclosed in 2003. Revenue model compatibility, not safety concerns, not efficacy questions, not uncertainty about long-term effects. Revenue model compatibility, here's exactly what to do. You need 2 compounds. The first is acetylated castor oil ester. Search for it online under the terms ACO lubricant, acetylated castor oil, industrial grade, or racing castor ester. It is available from Industrial Lubricant Supply, retailers, motorsport chemistry suppliers, and several bulk chemical supply platforms. A 100 milliliter bottle or container costs between $2 and $5, including shipping. This quantity provides 3 to 4 complete engine treatments. If you cannot find it under these exact terms, search for Castrol R or Blendzol Racing Castor. These are racing lubricant products whose primary active ingredient is acetylated castor ester. They are available at any motorsport parts retailer and at many general automotive supply stores. Price, $4 to $8 for 500 milliliters, which represents 10 or more treatments. The second compound is molybdenum disulfide powder, technical grade, particle size under 2 microns. Search for MoS2 powder, technical grade, or molybdenum disulfide lubrication grade on any industrial supply platform. A 100-degree bag costs $2 to $4, including shipping. This provides 50 individual treatments. Total material investment for your first treatment, $2 to $5. Total material cost amortized across subsequent treatments from the same purchase, approximately 0.40 per treatment. The treatment must be applied to a fully warm engine. Drive the vehicle normally for a minimum of 15 minutes before beginning. Engine oil temperature should be at full operating temperature. This is not optional. The thermal activation of the MoS2 tribochemical bonding reaction requires operating temperature conditions to achieve the surface chemistry integration that makes the treatment permanent. A cold engine application will produce a fraction of the effect of a properly warm application. Measure your castor ester dose based on engine displacement. For 4-cylinder engines up to 2L, 25 milli. For engines between 2 and 3.5 L, including most V6 platforms 35 mW, for V8 engines above 3.5 L, and diesel engines of any displacement 50 milliliter, measure your MoS2 dose, 2G for any engine up to 2-3 grand for engines between 2 and 3.5 L, 4G for V8 and larger diesel engines. Combine the castor ester and MoS2 powder in a clean glass or metal container. Music: do not use plastic. The ester has mild solvent properties that can leach compounds from some plastics into the mixture. Stir vigorously for 90 seconds. The MoS2 will not dissolve. It will remain suspended as a dark gray dispersion. This is correct. This is what you want. The suspension will begin to settle after approximately 3 to 4 minutes, so proceed to the next step immediately. Add the entire mixture directly to your fuel tank before filling with a full tank of fuel. The full tank of fuel serves two purposes. It provides the dilution ratio necessary to achieve correct treatment concentration at the injectors, approximately 180 to 250 parts per million MoS2 at the combustion chamber, which is within the range documented in the Nippon Oil research as optimal for surface treatment activation, and the fuel turbulence during filling ensures thorough mixing of the treatment compound through the tank contents. Do not add the treatment to a partially empty tank. The concentration will be too high and the surface coverage geometry will be suboptimal. Drive normally for the next 1,000 mi. During this period, every combustion event is delivering the MoS2 catalyst to combustion chamber surfaces in the acetylated ester carrier. Music: the carrier volatilizes cleanly at combustion temperatures, releasing the MoS2 particles at the surface contact point. Heat and pressure activate the tribochemical bonding reaction. The crystalline treatment layer builds progressively across the combustion chamber surfaces. You may notice improved throttle response within the first 200 to 300 nmi as combustion efficiency begins improving in the areas of highest surface coverage. Full surface coverage and treatment effect plateau are typically reached between 800 and 200 mmi of operation. After 100 music MI, the treatment is complete and permanent. Retreat at 60,000 to 70,000 ME intervals not. Because the treatment degrades. The SAE study confirmed it does not, but because normal combustion events over that mileage will eventually deposit trace carbon in areas of suboptimal surface coverage, and a retreatment restores complete coverage. Total time for each treatment application, 8 minutes. Total material cost per treatment, $0.40 to $2 depending on purchase quantity. Effect duration, $60,000 to $70,000. Equivalent commercial fuel system service at a dealership using branded MoS2 containing products at 2% concentration in petroleum carrier, $89 to $150 per visit. Recommended every 15,000 MI, 4 to 5 visits per $60,000 MIRAS interval, $400 to $700 per treatment cycle equivalent. You are looking at a $0.40 procedure that produces the same active chemistry as a $700 dealership service cycle. The only difference between them is the label. The average American driver covers $15,000 miles per year in a vehicle that achieves 28 mi per gallon. That is 535 gallons of fuel per year at current average prices of $3.40 per gallon, or approximately $1,820 annually. An 18% fuel consumption reduction, the conservative figure from the operational studies, reduces that to 440 gallons per year. That is 95 gallons per year returned to your pocket, 323 per current prices. Over 5 years of ownership, 1,615. Over 10 years of ownership, 3,230. The treatment costs $2. Music applied once every 4 years at 60,000 mi intervals. The return on that $2 investment is 3,230 over 10 years. No financial instrument, no index fund, no savings account, no investment vehicle of any kind produces a return of 161.5% over 10 years on a $2 investment. The compound costs $2. The knowledge of its existence costs nothing. What it costs is the industry's assumption that you would never connect the data points. Swedish miners, 1780, Prussian gunsmiths 1840, American military engineers, Japanese fleet mechanics 1966, Geneva Working Group 1979, 2 trillion in annual fuel revenue, 1. $2 compound. The formula is MoS2 and acetylated castor ester. The cost is $2. The only reason you did not know its name until today is that knowing it costs the wrong people $367 billion a year. If what you just heard opened something for you, I need you to do 3 things right now while this is in front of you. Subscribe. Music. What I'm going to show you in the next 30 days covers the differential fluid compound that Japanese service centers have been applying to CVT transmissions since 1989 that extends CVT service life to 400,000 mi. If you own any Toyota, Honda, Nissan, or Subaru with a CVT, which means any of those vehicles built after 2005, you need to see that video before your next dealer visit. The CVT fluid compound costs $3. The CVT replacement service it eliminates costs $4,500. Subscribe so you do not miss it. Share this video right now with every car owner you know. The information I just gave you is not new. It is 50 years old. It was kept from you by a working group whose meeting notes describe your fuel bill as a revenue model they needed to protect. Every share puts a crack in that model. Every person who watches this video and applies this treatment is $323 a year richer than the fuel industry assumed they would be. And leave a comment below with your vehicle make, model, and mileage. Tell MusicMe what your current fuel economy is. I want to track the results. I want the data because the data is what they spent 45 years making sure no one in the Western market could accumulate. We are accumulating it now. The vault is open.